So we have been studying uniform circular motion, and we know that an object that is going around in uniform circular motion has an acceleration, centripetal acceleration, which is v square by r. Correct? We can write it as v omega r, omega square, whatever, but v square by r. Now, if an object has an acceleration, what does Newton's second law say? It must have a force. How much force? It must have a net force, I'll just call it F, must be equal to mass times the acceleration. So mass times v square by r. This in fact must be the net force acting on it. We usually represent this quantity or call this quantity centripetal force. Because this is a centripetal acceleration, we write centripetal force is mv square by r. It is nothing but mass times acceleration. Okay. Now this is a very bad name and we will see that in a minute. But basically, let us think about the direction of this force. Why is there a force? Because otherwise this fellow will not have an acceleration. It has constant speed but not constant velocity. So its velocity is changing. So the velocity is changing like this. As it's going, the velocity is changing. When the object is here, it has an acceleration in this direction. So it must have a force. The centripetal force must be pointing towards the center. So that's why we call it centripetal, because the force must basically point towards the center. So we call it centripetal force. When the object is here, the centripetal force is upwards. When the object is here, the centripetal force points towards the center. So this is the direction. There it points this way. If you are here, it points that way. It's always pointing to the center because the acceleration is pointing towards the center. V square by r is always pointing towards the center. This is just mass times v square by r. Okay. Let us think about this. But the force is perpendicular to the velocity. How can an object have this velocity and a force like this? How can this force make the velocity change and go in a circle? So that is sometimes not that clear. So let us draw this situation. Now imagine this object has a velocity v. Now if there was no force, this object would have come there. By exerting a force F, what am I doing? This object which should have gone there, I am using this force to basically bend the velocity. Also I am going to move it from here to there. So this fellow, instead of being here, is going to land up somewhere there. And this fellow would have moved on this path. What made you go down like this? Instead of going straight, why did you go down? Because of this force. And now my velocity is in this direction. Because if I had this velocity and this force basically pushed me down, my velocity turns. So my velocity has turned. What used to be this velocity is now this velocity. At this point, I am not exerting the force like this. I am going to exert a perpendicular force. Notice that every point, the force is perpendicular to the velocity. This is the velocity, this is the force. This is the velocity, this is the force. This is the velocity, that is the force, right? Acceleration, centripetal acceleration is always perpendicular to the velocity. So A times mass times centripetal acceleration, ma, must also be perpendicular to the velocity. So that's what we are calculating. So now suppose I exert a force, let me call this Fc. Now this guy should have gone there, but because of this force, this guy is going to land up here. Can you see that? This force is basically, instead of going there, it is actually pulling you this way. So you land up here. And instead of the velocity being this way, by the time it reaches here, the velocity has turned in direction. So what has this force done? It has turned the velocity. Here the velocity was like this. This force has turned it. This force, this way, this force has, think of it applied here. You can see that this is what it's doing. So it is turning the velocity. So now here I have this velocity. Now this force applied perpendicular to the velocity. At every point, you can see that the force is perpendicular to the velocity. Now this is where I should have gone, but this force basically takes me there. And so I go like that. And now my velocity is this way. And now if I apply a force like this, it's going to turn like this and so on, and it's going to come back. Okay. So you can see that the force perpendicular to the velocity is actually turning the velocity. So the velocity was like this. This perpendicular force is turning the velocity. That's what is happening here. So here is the velocity. You can either think of it as basically pushing from the top or pulling from the bottom, it doesn't matter. Basically, it is going to make the velocity bend around like that. Let us understand this again a little more carefully. So, if I look at this force, sorry, this is the velocity, and I look at this force, force produces an acceleration. Force is equal to ma, but F by m is acceleration. It produces an acceleration. So, acceleration into time, if the direction of force is like this, the acceleration direction is also like that. You are doing this. So, can you see that the velocity vector has turned? Correct? What used to be like this has turned. If I had this velocity vector and I exerted a force in this direction, which means the acceleration will be in this direction, it would have produced an AT, acceleration into time, and look at the velocity vector. The new velocity vector will be in the same direction, it would have become longer. If the force was acting in the opposite direction, the acceleration will be in the opposite direction, and so I would have added an AT. So V and then AT would have changed it, and so now I would end up with a shorter velocity. But if I had a velocity like this and my force was like this, right? So it will basically produce an acceleration in the perpendicular direction. What does perpendicular force do? It turns the velocity. So this force turns the velocity. This force turns the velocity. Okay? Think about it, it's not such an easy idea. Now I want you to understand something else. It's all nice to call this centripetal force, but it's a very, very bad term. Why is it such a bad term? When I say gravitational force, I mean Earth is pulling this chalk down. Gravitational force, what is the source? Earth. Earth's gravity is the reason this force comes down, right? This object comes down. Similarly, when I say I am exerting a tension force, the rope is pulling that object. Normal force, the surface is pushing that object. Friction force, one surface is trying to prevent rubbing. So every force, when we use the word something force, right? Usual electric force, you mean electricity is the source of the force. So that gives us this feeling that centripetal force comes because the object is going in a circle. But that's a very bad idea because it's not true. Centripetal is not the reason for the force. This is not the source of the force. Okay, it's a very bad terminology. In fact, this is not even a force. It is an acceleration. You have centripetal acceleration. Okay? Then why do I call this a centripetal force? There must be some other force which produces the centripetal acceleration. That some other force could be tension. So centripetal force could just be tension. It could be mg. It could be something like, let us say, electric forces. It could be friction. It could be normal force. It could be any of those various forces that we know, spring force and so on. But these are all forces. For example, spring force. Who produces spring force? Spring. Okay. Who produces centripetal force? Spring. Right? Centripetal force is not produced because it's moving in a circle. It is the other way around. It is going around in a circle because there is somebody else pulling it, and that somebody else produces a centripetal acceleration. This is centripetal acceleration. That is correct. Okay? This is not even a force. So people assume that whenever you're going in a circle, because you're going in a circle, you produce a force. Terribly wrong. That is not correct. Because you have a force, you go in a circle. Don't mix the cause and the effect. Okay? There is some other force, and we usually will call it net force. This itself may be sum of lot of forces. Like you might have F1 plus F2 plus F3. You might have multiple forces acting on this guy. For example, there might be somebody pushing it like this. There must be somebody pulling it like this. So F1, F2. Right? F1 plus F2 is the net force acting on it. That net force produces V square by R. So this is equal to m times the acceleration, which is V square by R. So this whole thing is called centripetal force. It is not this or this or this. There is no single force called centripetal force. I hope that is clear. So there is no such thing as centripetal force as a special kind of force. It is not a special type of force. Okay, so let me mark it very carefully. This is not a new kind of force. In fact, it may not even be one force. There may be no single force in a problem which you can mark and say, hey, that is centripetal force. Like for example, if I say F1 and F2, F1 plus F2 produces centripetal acceleration. So is F1 centripetal force or F2? No, the sum total, right, the net force, we are just giving it a name saying this net force is centripetal force. Okay, but that's a very bad terminology. I will use it because everybody uses it. What is good is to say the net force produces a centripetal acceleration. Second, I want to also just keep this in mind. Whenever we solve problems with Newton's laws, you know that when we say net force is mass into acceleration, let's say this is a block, I have F1, F2, F3. So F1 plus F2 minus F3 produces an acceleration A. Is MA a force? No. A is the result of these forces. So MA is not actually a force. I keep insisting that you should not treat MA as a force. This is not a force. This is net force, sum of all the forces. This is a force, somebody produced it. This is a force, somebody produced it. This is a force, somebody produced it. MA, nobody produced. All of these forces together produced acceleration A. Newton's law just allows us to calculate the acceleration like that. So it is not like MA was produced by some particular kind of object or something which actually produced MA. MA is the result of forces. So you should not even treat them in the same level. This is MA. Think about it. This is MA, right? This is the acceleration. So there is no such thing as a centripetal force. We will ask what is the value of the centripetal force, but that just simply means you are asking what is the net force acting on the object, okay, in the centripetal direction, because the net force is equal to mass into centripetal acceleration, right? So centripetal force, remember always, is not a force or produced because somebody is going in a circle. It is actually forces like tension and other forces that add up to make the object go in a circle. So the net force is basically what we call centripetal force. So now let us look at this question. So in this question, there is an object that is connected by a rope to the central point, and this object is going around in a circular path. It's a horizontal circle. Okay. Now imagine that I am showing you the situation with this mouse. Okay. This rope is connected to this mouse, and I am going to make it go around like this. Assume that this was a horizontal circle, right? So now this object is going in a circle. What is pulling it in? What was the force pulling it in? The wire, right? So this wire is pulling it in with a force. We can call it the tension in this wire. That must be the reason it is going around. So that only force acting on this fellow is T. So T must be the centripetal force. The centripetal force must be the tension T. Notice when the object was here, the wire is pulling it like this. When the object is here, it's pulling it like this. When the object is there, it is pulling it in this direction. Okay, when it is there, it is pulling it this way. It is always pulling it towards the center. Okay, so now the question says that the time period, I am using small t because tension, again capital T, will be getting confused. So we'll use time period small t. Okay, so that is 5 seconds. It takes 5 seconds for this fellow to go around, which basically means omega is 2 pi by the time period, 2 pi by 5 radians per second. So that is the angular velocity. And this means the acceleration, centripetal acceleration, which actually is in this direction, and when the particle comes there, it will be in this direction, right? If it was here, it will be in that direction. So what is the centripetal acceleration? Centripetal acceleration, you can use r omega square. R is 2, omega is 2 pi by 5, so 2 pi by 5 square. So this is 2 into 4 by 25, 4 by 25 pi square. Okay, so this is 8 by 25 pi square. So this is the acceleration in meters per second square, and so the tension must be mass into acceleration. What is the mass? 5 kg. Acceleration 8 by 25 pi square, and so if I cancel that out, I am going to get 1.6. 8 by 5 is 1.6 pi square. So the tension value is 1.6 pi square newtons. Okay, this is that value of the tension. So what is the force acting on it? The only force acting on the body is the tension force. Now this tension force is what we will call in this problem centripetal force. So suppose I ask you, hey, tell me what is the centripetal force. What force are we talking about? Tension. In this case is tension. Right? It is not like this force is a separate force and equal to tension. This is the only force that is there. So centripetal force in this problem is the tension equal to 1.6 pi square newtons, right? Now, generally pi square is approximately 9.8. Suppose I call it approximately 10, then we can call this centripetal force or tension in this case 16 newtons for calculation purpose. Not so important. 1.6 pi square newtons is good enough. In this question, there is a hemispherical bowl, okay, and very smooth one, let's say. And from the top, it gives a body, this mass block, mass m. You give it a velocity, which we don't know. What we know is when it reaches the bottom, it has a speed of 4 meters per second. So we know that. This radius of this thing, this hemisphere is basically 2 meters. That's also given. And mass of the object is 10 kg. So all of this we know. We want to find out what is the centripetal force. We also want to find out the normal force. Let us think about this. Now this object must have a centripetal force. Without thinking, I can just write it must be mv square by r. Correct? Now what is m? M must be 10 kg. V is given, it's 4, so 4 square. R is 2 meters. So if I look at this, 16 divided by 2, that is 8 into 10, 80 newtons. So I know that the centripetal force is 80 newtons. What direction is the centripetal force? Upward direction. It has to be in that direction. Now, don't start assuming therefore that there is such a force. Because let us think about this M. If I look at this block M, it has two forces acting on it. One force is the gravitational force pulling this fellow down. Then this floor is going to exert a normal force. There is going to be a gravitational force and there is going to be a normal force. There are only two forces. There is one force which is N, right? That is this force. And there is this force mg. And how much is mg? M is 10 kg, g is 10. So basically this is 100 newtons. So there are only two forces, N and mg. Now that's it, that's all. There is no centripetal force. N minus mg is the net force in this direction. Is that a new force? No, it is just the sum total of these two. So who is acting, who is exerting this? Nobody. There is somebody exerting N, there is somebody exerting mg. The sum total of these two is N minus mg. The net force, let's say, is pointing in that direction. This must be equal to mass into acceleration v square by r. Now, this we have already calculated, mv square by r, that is equal to 80. Correct? Because v square by r, we know it's 4 square by 2. So that is 16 by 2, 8 into 10, 80. Now, n minus mg, which is 100, is equal to 80. So this says that n must be 180 newtons. There is a normal force of 180 newtons in the upward direction. And the net force is 180 newtons upwards minus 100 newtons downwards. So it is 80 newtons upwards. This is what we were calling centripetal force. So the net force is 80 newtons upwards because the net force is the same as the centripetal force. There is no such thing. If you look at the free body diagram of the object, there is no centripetal force. There is a normal force, there is a gravitational force. That's all. There are only two forces. The two forces together produce the centripetal acceleration. These two forces together produce that v square by r. Always you will find that you need to find out what force produces or what forces together produce the centripetal acceleration. The sum total of all those forces, we will call it centripetal force just for convenience. There is no such separate force. This force is not there. This is just the sum of these two. If you look at the free body diagram, the centripetal force cannot be drawn on the free body diagram because it's not a special kind of force. So I hope you have now understood the idea behind centripetal force. The best way to really understand this is to do a whole bunch of questions where you can apply the concept and understand it yourself well.